This is Mr. Sandell, and we're talking about perfect self-similar fractals today. To begin with, in the first part of this lesson, at least up until this part, we will be rooted in the real world, but that's basically all there is. And then we're going to be in the math world, where things are perfect and you can't actually see or touch things. So to begin with, imagine you have metal. Sometimes the metal is a really thin wire, sometimes the metal is this flat sheet, sometimes the metal is this cube of metal over here, and then sometimes you have this mesh of metal. My question is, if I multiply each of the lengths of the original shape by 2, what factor will the mass increase? So with a thin wire, if I multiply by 2, then I have 2 thin wires. So when I multiply length by 2, the mass is scaled up by a factor of 2. What about with a flat sheet of metal? With a flat sheet of metal, again, I'm only talking about the length. You notice that I have the length here of 1, and now I have that length that is multiplied by 2. When I multiply the side length by a scale factor of 2, the mass scales up by a factor of, well, there's 1, 2, 3, 4 of those pieces, so that mass has gone up by a factor of 4. And again, with the cube, again, I'm just looking at that side length. That side length has now gone up by a factor of 2, still the scale factor of 2, yet the mass of the object has gone up by a factor of 1, 2, 3, 4, 5, 6, 7, and there's a hidden 8th one behind here, so the mass scale factor has gone up by a factor of 8. And then what about for a Sierpinski mesh? For a Sierpinski mesh, again, I have 1 side length, and now I have 1, 2 side lengths. So again, my scale factor is still 2. The mass scale factor, I have 1, 2, 3 of those original triangles, so I have multiplied it by 3. So this is actually really interesting. When you look at the scale factor, if you raise it to the power of the dimension, it's right here, dimension. If you raise it to the power of dimension and then multiply it by the mass, that's the same as multiplying the mass by the mass scale factor. And if you divide both sides by mass, you can get rid of this and you can say that the scale factor to the power of the dimension is the mass scale factor. So now from here on out, we're going to be staying in math land. Therefore, everything is in our head. There's no actual thin wire. We've just changed to the word line. There's no flat sheet. It's a square. There's no solid cube of metal. It's just a normal cube, and there's no Sierpinski mesh. It's a Sierpinski triangle. So I always tell my students the philosophy of math you can't ever touch. There is no such thing as looking at a perfect circle. If you zoom in and zoom in and zoom in and zoom in at a perfect circle, eventually you're going to be made out of atoms. Those atoms aren't in a perfect circle. They're not infinitely thin. So everything from here on out only exists in our mind, and I'm doing my best to explain what's going on in our mind while we have paper. So my question is, what power does 2 need to be raised to in order to get 2? And hopefully you know that 2 to the power of 1 is 2. Therefore, if I'm using my equation up here, I'm trying to figure out what dimension a line is in. Well, because I raised it to the power of 1, raising it to the power of the dimension means that the dimension is 1. Same thing for the square, right? So for a square, 2 to what power is 4? Well, 2 to the power of 2 is 4, therefore we're in the second dimension. For a cube, what power does 2 need to be raised to get to 8? Well, 2 to the third power is 8, therefore it's in the third dimension. And this is where things get a little bit wonky. So for a Sierpinski triangle, again, all of these base scale factors, the side length just went up by a factor of 2, but this mass scale factor that we figured out from the problems up above are going to be a little bit harder to get to, because 2 to what power is 3? The problem is we don't know. You can go ahead and put a question mark right here, but what I usually say is go ahead and guess. What dimension do you think we're between? Because we know that we're somewhere between 2 and 4 because we're in 3. So a lot of students will say, well, we're in between 1 and 2. Since 2 and 4 is kind of like that 3 is a halfway point. Maybe the answer is maybe 1.5. So you might want to guess 1.5. And whenever we guess in my class, we do a question mark. So maybe it's 1.5 question mark. It's a guess. We don't know. We can come back and guess and check the intuition. Is that right? So here's how you actually solve that. And this is like if I were doing a normal set of lessons, I would usually have students write this all out. I've written it out in advance so that way you can kind of take a shortcut and see the real math, because a lot of my students will do this lesson where they don't understand what this tool is. So if we say that D is the dimension and we want to know what the dimension of that shape is, we don't know this dimension of the shape. We have a question mark, right? So to find that dimension, we're going to be solving this equation 2 to the power of d is equal to 3, which looks like what we have up here. We're going to call this the dimension. So 2 to the power of d is equal to 3. That's the same thing. I just rewrote it down here. The only way that we can solve this equation is by using logarithms. For those of you that have never touched or heard about logarithms, it's basically a tool. It is technically the inverse of a power. I always call them the what power functions. What power should you raise to in order to get a certain result? So if you know logarithms, if you're in maybe an Algebra 2, a pre-calculus, or an AP calculus class, you'll know that one of the properties of logarithms is this. If you have log of a to the power of b, it's the same thing as b times a, or b times log of a. So you might be seeing that and it's like, there's a bunch of gibberish, Mr. Snell. What does that actually mean? Well, there's two things that are really important here. First, b was on the inside, and now b is on the outside. The second thing that's important to know that b was a power, but now b is being multiplied. It's no longer a power. So those are the two key parts of a logarithm that'll be really helpful to us. And that's the whole point of using a logarithm, is because we can get that power down and kind of rescue Rapunzel, who's trapped up in here in the tower. So again, we're trying to solve 2 to the power of d is equal to 3. That's the original problem. And we're going to take the log of both sides. Whatever you do to the left side, you do to the right side. Kind of one of the universal truths of solving equations in mathematics, right? And then here's that property. Remember that d was on the inside, and then we pull d to the outside, and now d is on the outside, and it's being multiplied. We're using this property. You're using that property that I just talked about. And this is usually pretty straightforward for people. If I have a variable that I'm trying to solve for and it's being multiplied by something, the opposite of multiply by something is to divide by that something. So we're going to divide both sides by log of 2, and log of 3 divided by log of 2 it's about 1.585. Again, in my class, let's always round to 3 decimal places. That'll prepare us for the AP test if you're heading in that direction. So what does this mean? We have found the 1.585th dimension. The Sierpinski triangle has a non-whole number dimension, which is weird to think about, right? We think about things as either in the first, second, or third dimension. There's no in-between. And if there is in-between, why do we have this yucky number that we have to round? Yeah, it's weird, but that's the whole idea behind fractional dimension. So I would like to make this more general for you guys so you can do the problems that are about to come up. So just to give you a heads up, we're going to have problems that look like this. I'm going to ask you, what is the fractal dimension of the Cantor set? What is the fractal dimension of the Sierpinski carpet? What are the fractal dimension of the Menger sponge? We have all these that we are about to solve. You should know how to do them really quick. So let's try to make a formula, right? A generic formula. So again, we're going to be solving for the dimension. So here's the dimension. In general, we're going to have this formula where we have log of something divided by log of something. You always have logs on the top, logs on the bottom, and then some students will look at their calculators and say, I have a log base 10, Mr. Sindel. Will that work? The answer is yes. As long as it's the same log base 10 on the top and the same log base 10 on the bottom, that'll work. Some people say, oh, I see an ln button. Will that work? As long as you do ln at the bottom, that also still works. So we're going to say that n is the number of self-similar pieces, or you can just say that this is, a lot of students will generalize this and they'll just say it's log of the number of pieces like that. And then s is the scaling factor of the size of the sides. So size of the sides, definitely an s right there, right? So to give you an example, let's take a look at the Koch curve. And I did cut this off a little bit too close to the top, but it does start with just a straight line. And if you're familiar with the Koch curve, you might be familiar with the Koch snowflake as well, which is, instead of a line, it starts with a triangle. But anyway, we're starting with a line just for the curve. Notice what we've done. From the first iteration to the second iteration, a change has been made. It seems like there's been like a triangle added almost. But that's not really the way you want to think about it for calculating a dimension of this fractal. What you really want to be thinking about is how many self-similar pieces are there? Well, there is 1 piece, 2 piece, 3 piece, 4 pieces. So therefore, n is equal to 4. The top of this fraction is going to be log of 4. And then you want to say, well, how big is that piece? And that's a lot harder to do, especially since we don't have the formal definition of the fractal. If we had the computer program, we'd be able to say, okay, well, that length is exactly 1/3. But because we don't have that in front of us, we're going to do some wishy-washy math and say, well, we're going to go ahead and eyeball it, right? It's not super technical math, but a lot of these you can eyeball pretty well. The best way to eyeball this one is to draw the original, whoa, my pencil's definitely not working there, to draw the original line underneath and say, okay, well, including the white space, this is clearly cut up into 1, 2, 3 sections here. This first section is 1/3 of the entire length of the line, eyeballed, of course. Therefore, you can say that the scale factor is 1/3, or you kind of really take the reciprocal and you say it's a reduced factor of 3. So you come down here and say that this is log of 3. And therefore, this dimension of this Koch curve is log of 4 divided by log of 3, which is 1.262. So now is a great time to show how to do this on the calculator. So let's go ahead and open up our calculator. For our calculator today, we're just using a scientific calculator. Let's go ahead and clear everything out of this. I like my calculator on the left-hand side because I'm right-handed. I want to be able to write in a way that makes sense. All right, so how do you enter this? You can do it a few different ways. You can go to the function tool and then hit the log button. You can say log of 4, and then that whole thing divided by log of 3. So let's go back to the function. You do log of 3. You do get the right answer, right? It's 1.2618, and then the 1 rounds up to a 2 because it's followed by an 8. That's one way to do it. Another way to do it is to actually type out LOG, and that will also turn into a log function. Something that a lot of students don't realize is Desmos has the built-in feature that auto rounds for you, which maybe makes you stupider because you're doing less thinking, but I just want to demonstrate that you can do it. So if you type in ROUND, it's the rounding function, and if you just start your parentheses here, it says round to the nearest whole number, which we don't want to do. We're going to do a comma here. So we'll say comma and round to 3 decimal places, and it will round it to 1.262. So I'm going to cheat and just have it auto round for us. I hope that you're okay with that. If you really want your students to learn how to round, then maybe you shouldn't do this. All right, so we have a formula that's ready to go. All we have to do is we have to replace the 4 and we replace the 3, and we're good to go. If you want to be super fancy, you can go like this. You can say, treat this as a variable, right? We'll call this variable, we might as well just call it a capital N, because why not, right? Capital N, that's the exact formula. This 3 down here, I'm going to call that a lowercase s. If you do that, then you can come down here and you say, okay, well, capital N is equal to 4 in this case. So I can come down here and say it's equal to 4, and I can say that lowercase s is equal to 3. And I can just control the variables down here with these 2 boxes without having to ever touch this formula up here, and it will automatically round for us. Really, really fancy, right? All right, so let's try some examples. So I did, by the way, try to organize this from most famous to least famous fractals, and it is a very opinion-based question, but I think that the Sierpinski triangle is the most famous. I think that the Koch snowflake or the Koch curve is the second most famous, and the Cantor set, therefore, is the third most famous, fourth most famous. If you disagree, I'm curious to hear what you think is the most famous. So let's try the Cantor set, right? So again, the generalized formula is I'm going to say that the dimension is equal to, it's going to be log of a number divided by log of another number. That first number on the top is the number of pieces. So I can see that it originally starts out as 1 piece, and then it turns into 2 pieces. And you can see at each iteration as you go down, it multiplies by that. So it was 2 pieces. If I multiply by 2 again, it's 1, 2, 3, 4 pieces. And then multiply by 2 again, it's 1, 2, 3, 4, 5, 6, 7, 8. So I'm definitely breaking it into a factor of 2 in terms of the number of pieces. So I'll say log of 2. Each piece turns into 2 more pieces. And then how big are they? Remember that this bottom one is the size factor. So this is helpful if you draw the entire line, which the entire line is already up here. So it's kind of nice. So this line, and then there's like an empty space that's the same length, and then there's a full line. So each of those is 3 lengths. So I can say that the scale factor, you're getting 1/3 as big. So I'm just going to take the reciprocal and say that that's 3. So log of 2 divided by log of 3. I'm going to come up here to my fancy calculator and say log of 2 divided by log of 3. I don't have to change that. And I get, this is approximately, so I'm going to do wavy equal to sign. That means approximately. I'm rounding to 0.631, which is interesting, right? It's always fun to come and analyze what this means. Remember that if you're in the first dimension, that's a line. This is less than a line. It's less space filling than a line, or it's less, maybe we're using the definition of roughness. It's less rough than a line. Oh no, for this lesson, it's probably more apt to say it's less space filling than a line. I mean, look at this down here. That doesn't even look like a line anymore. That is definitely a line, but this stuff down here is not a line. And I know I'm talking, I really should talk about number 2, but I love to teach about math. So the other thing you want to think about is technically the Cantor set, you see the iterations. The Cantor set is when this goes to infinity. These are like, this is a pseudo Cantor set. This is another pseudo Cantor set. This is another pseudo Cantor set. It's showing you how it's created. The real Cantor set is the one that actually goes all the way to infinity. And that one that goes to infinity has this dimension of 0.631. All right, what about the Sierpinski carpet? So then we get some harder questions. So now I'm kind of starting with this 2-dimensional object. With this 2-dimensional object, I'm counting how many of this shape do I see in the next image. So I see one of those pieces there, 2, 3, 4, 5, 6, 7, 8. There's a total of 8 of those pieces. Don't accidentally count empty space as that piece. They have to be self-similar. That's the whole point of this lesson, self-similar pieces. So in this case, I'm going to say for my work that my dimension is equal to, oh, it's not working. Okay, so it's going to be log of how many pieces? I saw 8 pieces over log of, okay, I have to be really careful here. For my scale factor, it's always talking about side length. It's not talking about area. So the side length, remember up here, I used to have a side length of 1, and now it's 1, 2, 3, meaning each of these pieces is 1/3 in terms of its side length shorter. So I'm multiplying by 1/3. And then I always take the reciprocal and say that means I'm reducing by a factor of 3. And then come down here. The bottom is 3 again, so I don't have to change that. I can just say that n now is 8. And that means I'm living in the dimension roughly. Again, I'm approximating, I'm rounding to 3 decimals. It's 1.893, which is really, really close to a space filling curve. It's really close to a dimension of 2. If you're a dimension of 2, you're just talking about area, right? This is really close to area, but we can see there's holes. All those holes, when this eventually goes to infinity and becomes the real Sierpinski carpet, it will be full of holes, and therefore it doesn't perfectly fill the second dimension. All right, let's try something that's a third dimension. Okay, so you're kind of expecting, this is like the Sierpinski carpet, but in 3D, right? It's very, very similar. You can see that that shape looks like that shape. You can say that shape looks like that shape. They're really close to each other. So we're, again, going to set up our formula. It's the same formula over and over. I might as well copy it and paste it into all of these, right? The dimension is equal to log of a number divided by log of another number, and that will have its decimal approximation. So I'm just going to be lazy. I'm going to go ahead and grab you. I'm going to copy you. In fact, I can probably just duplicate you now. So grab you there, duplicate you again down here, and keep pasting over and over again. Paste and paste. All right. So coming up here for the Menger sponge, I need to count the number of self-similar pieces. So the piece size is this cube. How many cubes do I have? It's a kind of a hard task, but let's look at the front side. We'll count that one first. Then we'll look at this back side back here, which you can not really see, but we'll count that back side. So I'm counting 1, 2, 3, 4, 5, 6, 7, 8 in the front. If there's 8 in the front, there must be 8 also in the back. So I have a total of 8 plus 8. And then the pieces that connect, there's this cube right here that connects, right? I hope everyone can kind of see that that's the cube that connects. So there is that 1, 2, 3, and that fourth one right there. There are 4 pieces that connect. So plus 4. What do we have? 8 plus 8 is 16, plus 4 is 20. So there's 20 pieces. And then how big are the pieces? I'm going to go ahead and take a random guess. Mathematicians love log base 3, or log of 3 on the bottom for the denominator. Let's see. The original side length was 1. Now the side length, I fit 1, 2, 3 of those pieces. So each of these cubes is 1/3 as small. Take the reciprocal for the scale factor, and this is just log of 3. So don't change at the bottom, you just change the top to 20. And this is a dimension of 2.727 rounded to 3 decimal places, which is really cool. I love taking a step back and looking at what we've done. We had a 1D object that made something a little bit less than a 1. We had a 2D object that made something a little bit less than 2. We had a 3D object make something a little bit less than 3. So that's kind of the pattern, right? Let's see if that holds through. So I'm seeing that, oh, I have a 2D object. I'm starting with like area, and it's increasing and increasing with its progression, with its iteration. I'm going to just guess here that this dimension over here is going to be a little bit less than 2 since I started with the second dimension. I have all this empty space here. So let's see what happens. This one is a little bit harder, but remember, at each step, the number of pieces is kind of multiplied. So I'm multiplying by 20 to get 20 pieces, and then I'm multiplying by 20 again to get 400 pieces. There's 1, 2, 3, 4, 5, 6, 7, 8 of those, and then you multiply that again and again. So it's kind of like what you're multiplying by to get the number of pieces. So what's actually helpful for number 4 is to look at one piece and say that one piece turned into 5 pieces, therefore the number is 5 for the number of pieces of self-similar pieces. Or if you want, you could count all 25 of these and say, well, to get from 5 to 25, you're multiplying by 5. There's a few ways to think about that, right? And then how big are the pieces? Well, I originally had this length, and then I have this length. Notice that I have 3 of those pieces, so they're each 1/3 the size. Take the reciprocal, and you get 3. Log of 5 over log of 3. Let's see what dimension we're in. We're in the dimension of 1.465, which we guessed, right? We guessed something that was a little bit less than 2. And it makes sense that this fractal dimension is a little bit less than this one because there's a lot more empty space in this one compared to the empty space in the Sierpinski carpet. So it feels right that that's the right dimension. All right, so I have some issues with the H fractal that I've made on this worksheet. It's not technically correct. Let me go ahead and show you why the H fractal of this illustration is a little bit off. Technically, the H fractal starts with one line, and I left the one line on there. It's because it makes a really cool demonstration of what's about to happen when this moves to infinity. Again, this is not infinity still, and there's an issue with it, and the issue is this. Technically, there's a 1, 2, 3, 4 brand new pieces. I know a lot of people say, well, that's one new piece, and that's one new piece. Not by the definition of an H fractal, and that's why it's really important to have someone guide you through this like me, or to be able to see exactly what the definition of an H fractal is. There's a total of 1, 2, 3, 4 pieces, so there's 4 self-similar pieces. Apple Pencil, please work, okay? And then how big are they supposed to be? So technically, this one piece is supposed to be exactly half of the line. The reason that this is not is because otherwise the lines start running into themselves. Like this line and this line will start running into themselves, where they're right next to each other, and it's really hard to see and count on your own. So I made them a little bit smaller for the sake of making a cool illustration and being able to count, but that came at the sacrifice of being not accurate in terms of its length. But luckily, I'm here, and I told you it's supposed to be 1/2 and take the reciprocal, so the scale factor is 2. So then I come over here and I say, hey, and look at this. The bottom's not 3 this time. I have to change it. So the top is a 4, the bottom is 2, and look at that. It's exact. It's not even approximately equal to. I have to erase that and say it's equal to 2, which means this. We found a fractal, a self-similar fractal that has a dimension of 2, and this is, and you should probably write this down because this is really cool. This is called a space-filling curve, meaning that if you take this to infinity, remember that these are all pseudo curves. Once you get the actual H fractal, that means that this has gone to infinity. Once you go to infinity, it will exactly be a dimension of 2, meaning if you zoom in and zoom in and zoom in and zoom in and zoom in, you will never, ever, ever see white space. Yes, you can start with a line. You can start with a simple line in a pattern in such a way that no matter how you zoom in, all the lines are compressed enough with the power of infinity that it's actually area instead of just a one-dimensional object. It's so crazy to me that in math, you can construct such a diagram that you start with the one dimension, compact it tightly enough in a right pattern that can turn into the next higher dimension, the second dimension. All right. And then we move on to the hexaflake. Super cool looking, right? So for the hexaflake, how many new pieces we have? We didn't count the old piece because it was laid on top of the H fractal, but these are all brand new pieces. They're all smaller, so we count each of them. We have 1, 2, 3, 4, 5, 6, 7. So 7 pieces. So I can say log of 7 for the top, log of 7. And then how big are each of the pieces? It's a little bit inaccurate, but let's show you what I'm seeing. So I'm seeing that we have this original length. Wow, Apple Pencil's not having fun right now. So it's this original length of 1, and then there's 1, 2, 3. Therefore, that each of these length is 1/3. We go back to our old and friend log 3 for the bottom. So I'm going to change the bottom to log 3. I'm going to change the top to log 7. And I mean, just looking at this, it looks like it's a little bit less than the second dimension because I see like these little pockets of white space. So this is going to be 1.771. Again, we did round it to 3 decimal places. What about Cantor dust? So Cantor dust looks really similar to the Cantor lines, right? The Cantor set. This is just in the second dimension. So instead of starting with 1D, I'm starting with 2D. And you should think that when you go to infinity, this will be so dusty, so much white space. This should be a number that is definitely less than 2, but barely bigger than 1. There's so much white space in here, right? So let's try it. We have how many new pieces? We have 1, 2, 3, 4 new pieces. So, oh, whoa, go too fast. All right. So we have 4 new pieces. 4 new pieces, and each piece is how big? Well, the original piece is just 1 length, and now for the side length I have 1, 2, 3, so it's 1/3. Take the reciprocal, so that scale factor is 3. So log of 4 divided by log of 3 is 1.262. Look how close to a line that is. It's not even close to area at all. It's 1.2. Come on now, 262. And that makes a lot of sense because there's so much white space. Okay, moving on to the harder curves. So the Hilbert curves is one of my favorite. I think it's my favorite space filling curve. We'll talk about. I guess I gave it away, didn't I? But the way that you construct it is really difficult to explain. So let me do my best explanation that I can. The Hilbert curve, the first Hilbert curve comes from taking a square and dividing it into 4 different pieces. You go and you look at the center of each of those squares, and then you connect it with a line that looks like the first shape of the Hilbert curve. And you say, okay, yeah, that's where that one came from. Cool, I see that one. How do you count that one? Like, I don't even see this one shape. Do you count like that one shape and then that shape, and is that an upside down? Like, how many pieces are there? Okay, so here, let me show you the next one. So it's the same exact size of square, but instead of dividing it into 4 pieces, you divide it into 16 pieces. So like this. And then again, I'm going to have a Hilbert curve that is half the size, where I go Hilbert curve here, Hilbert curve here, Hilbert curve here, Hilbert curve here. And so, I mean, for the calculation, you're seeing, oh, okay, well, 1 piece turns into 4 pieces. I can see it clearly here. Here's the problem with this curve. This curve is always supposed to start in the bottom left and end in the bottom right. And you can see that that still works at the very end of things. It always starts in the bottom left and ends in the bottom right, no matter what. There's a problem, though, that needs to be fixed, and that's what the Hilbert curve has in its algorithm. Here's the problem. When you trace this, watch what happens. If you start in the bottom left and you trace through this thing, I don't know why the Apple Pencil wants to let go, then in order to trace, I have to go through, look at that, I had to go through itself, and I continue tracing. That's a problem. These two meet up kind of nice, which is kind of cool. Okay, so that one's okay. And I come down here, and then I have to come all the way back to this left-hand one, and they come all the way through. That just doesn't look nice. We had to go through ourselves. That's just inefficient, so no. There's a better way, and I'll show you that better way. Here's a better way to do this. You have the same size grid, still divide it into 16 pieces, and I noticed that these two connected really nicely together. So let's leave them. I'll say that this piece and this piece will leave, because those will be connected nicely. And I still have to start in the bottom left. I still have to start or end in the bottom right. So I can't move those squares. But what I can do is I can reflect over this diagonal. So this piece comes up here, and this corner comes down here. And what that looks like is this curve like this. Boom, boom, boom. So I'm still starting in the correct spot. And then this piece now nicely connects to this piece. Same thing in the bottom right. There's going to be like a diagonal reflection where this piece doesn't, it stays on the line of reflection, so it's not going to move. But these two flip-flop, and then it's going to look like this. I have a Hilbert curve like this. Okay, so watch what happens when I trace now. Again, I'm starting the bottom left. I trace, 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 and look how nicely that connects. It connects so nicely, connects so nicely, connects so nicely, and we get the next piece of the Hilbert curve, and that's where this one came from. So now that you know how a Hilbert curve is created, let's go ahead and try to calculate its fractal dimension. So we know that I can just paste, right? I still have it. Yes, okay, I still have this ready to go. So I know that there were originally 4 of these self-similar pieces, and I know that each of them was half as big, because instead of being this length that went between 2 squares, it had to go between 4 squares, so that's half of that. Well, I guess you had to reduce it by a factor of 2, so it evenly spread that. So it's going to be 2. And then I just come in here and say log of 4 divided by log of 2. Wait, that sounds familiar. That's a space-filling curve. It has an exact dimension of, come on now, 2. And again, I always like to say that all of these are pseudo Hilbert curves. The real Hilbert curve is the one that goes to infinity and actually has a dimension of 2. Kind of cool that you found another space-filling curve. This would, again, completely fill the space, and it has some really cool properties that 3 Blue 1 Brown does talk about in some of his videos, if you want to go check those out. So, time for another one, the Pythagoras tree. This one is mathematically, computationally heavy, so just be wary. So, for number 9, I see that it clearly, here, can I paste my formula that way I don't have to worry about you? Paste my formula. I think these all need to be smaller now, so let me just go ahead and just copy these down. Oh, I need to duplicate you. I'll put you right there, and then I'll do the same thing. If I paste, it's going to be a little bit too big, huh? I'll zoom you down. Okay, I have all my formulas ready to go. So for the Pythagoras tree, I see that the original shape is kind of like this Y-shaped piece, and then how many new pieces do I have? I have 2 new Y-shaped pieces coming off of that. So that the 2 new pieces coming off of it mean I have number of pieces as 2. And then the hard part is, what's the scale factor? Because you can't just eyeball this one. You have to know it for real. And the hard part about this one is it's not a whole number. It's not even I mean, it is a decimal, but it is a decimal that's hard to find just by guess and check. So here's the main thing that you need to know. Whoa, didn't mean to do that. The main thing that you need to know is that this length and this length are the same. It's a square, right? And this length and this length are the same. So in order to go from this length all the way to this length, or more rather, this length to this length, it all goes through this right triangle. So what I really want to find is the relationship between this length of the triangle and this side length of the triangle. What's the relationship between the hypotenuse and the side length? And that takes a little bit of math. And I have no idea where I'm going to be able to fit all that math. I'm just going to choose this white space, and if I zoom in, maybe it'll be good enough. So you have a right triangle that looks like this. It's a right triangle, so I'll label this. Let's go ahead and just randomly make a nice length, 1, and then what do you multiply in order to get to that length? That's the question, right? So if you know things about right triangles, and you know that this is a 45, 45, 90, you might know the shortcut to get from 1 to the side length, because these side lengths should be the same. It is an isosceles triangle after all. The shortcut is to divide by the square root of 2. But maybe you didn't know that. There is a way to derive it another way. And you do it like this. You say that both these lengths are the same length, x, and then you set up the Pythagorean theorem. I mean, the hint is in the name, right? This is the Pythagoras tree. Of course, we're going to use the Pythagorean theorem. So here's how you use the Pythagorean theorem. You hopefully know that a squared plus b squared is equal to c squared, where you say that the length squared plus the length squared, or I guess I should say the leg squared plus the leg squared is equal to the hypotenuse squared. And you can plug it in. You can say that the new leg is x now, the other leg is also x, and the hypotenuse now is 1. So how many x squared plus x squared is a total of 2x squared. So I said 2x squared is equal to, okay, 1 squared is just 1. And then I just need to undo PEMDAS to solve for x. First I get rid of multiplication, then I get rid of exponents. So I'm going to divide by 2, and I get x squared is equal to 1/2. And then to undo a power of 2, you square root both sides. So square root the left, then I square root the right, and therefore x is equal to the square root. And then this is another cool fact. I don't know if everyone knows this. When you square root a fraction, it's the same thing as taking the square root of the top and the square root of the bottom. Just a property of exponents that I can explain at a later date if you are confused. And hey, guess what? The square root of 1 is just 1, so this actually simplifies to 1 over the square root of 2. So do you guys remember how I've been saying over and over again that, oh yeah, the Cantor set, each of these is 1/3 the size, and you take the reciprocal and you get 3. Well, we have to do the same thing here. We know that each of these is 1 over the square root of 2 of the size, and we take the reciprocal of this to find the scale factor. This reciprocal of 1 over the square root of 2 is a fancy way of saying flip this upside down, and square root of 2 is on the top, and this is just square root of 2. So I have to come up here and say that this is 2, and this is the square root of 2, and look at that. It's a dimension of exactly 2. This lives in the second dimension. Again, we're assuming that it means when this actually goes to infinity, it lives in the second dimension. This pseudo Pythagoras tree does not have a dimension of 2 until it goes to infinity. But again, we found a space-filling curve that doesn't even feel like it fills the space, but once you go to infinity, it does turn into area, which is really cool, right? All right, time for Minkowski sausage, or what most people call the quadratic Koch curve. If the Koch curve sounds familiar, it's because we just did the Koch curve all the way back here. This is the Koch curve with like the triangle piece, but if you do a square piece, it's called the quadratic Koch curve. This one is pretty fast, pretty simple. Here we go. You start with a line. And how many self-similar lines do we have? We have 1, 2, 3, 4, 5, 6, 7, 8 of those pieces. So you can say that there's 8 of those pieces. And how long are each of them? Well, if I draw the old line on top of this one, I can say that there's 1, 2, 3, 4 pieces. So each of these line segments is 1/4 as large. Take the reciprocal and you say that's 4. So here we go. I'm going to come back here and say that this is 4 on the bottom. It's going to be 8 on the top. And you get a fractal dimension of 1.5. Which is really cool. This is exactly, this Minkowski sausage, this quadratic Koch curve is exactly halfway between a line and area, right? All right, number 11, the Sierpinski arrowhead curve. I'll be honest, I don't fully know the math behind this one, and I did eyeball it a little bit. I know the definition, that's good enough for me. So notice that you start with a trapezoidal curve. Count how many of those trapezoids do you have. You have one trapezoid there. You have another trapezoid there. Oh, do you see the one on the top as well? It's a total of 3 of those trapezoids, so therefore there's 3 equal pieces. How big are each of those trapezoids? It's hard to see, but I know the definition. I know they're supposed to be 1/2. So if it's 1/2, you take the reciprocal, it's 2, and you can say this is log of 3 divided by log of 2, and it's 1.585, and I'm hoping that rings some bells. Doesn't that ring a bell? Like 1.585. Haven't we heard you before? Wait a second. Doesn't that look familiar? Yes, it looks familiar. It looks like the Sierpinski triangle that we had up here. That also had 1.585. Because they look the same, they are the same fractal dimension, which is kind of cool that our math did agree there. All right, this is Mr. Sandell's favorite. I had to throw it on here. The Sierpinski tetrahedron. This is where, like, your mind will be blown. I hope it's blown. It blew my mind when I first saw this. So let's go ahead and first look at this tetrahedron right here. That one tetrahedron is going to turn into this piece of the tetrahedron right here. There's one piece that turned into 1, 2, 3, 4 pieces. So I have 4 self-similar pieces. And then what was the side length? The side length used to be 1 there, and now it's 1, 2 there, just for the side length. You don't do area, you don't do volume, it's side length. So it's going to be log of 2. And you might be thinking, wait, Mr. Sandell, we've done log of 4 divided by log of 2 a lot. We've been doing it up here for the Hilbert curve. We did it for number 5, the H curve. But just in case you forgot, log of 4 divided by log of 2 is 2. And I know that a lot of students are like, cool, a number. Here's why that's crazy to me. It's absolutely ridiculous to me. You started with a 3D object, and this fractal lives in the second dimension. Over here for the H curve, we started with a 1D object and also ended in the second dimension, in area. How is it that you can start with a 1D object, you can start with a 3D object, and depending on the pattern that you fill that space with self-similar shapes, you get the same exact dimension? It's mind-blowing to me. Isn't that crazy? Anyway, let's answer some questions. Now, we don't need a calculator for this. So some of our fractals had a dimension between 1 and 2. What does that really mean for something to be more than a line and less than a plane? And the general idea here is it's more space filling than a line, but at the same time, less space filling. Space filling than a plane. A plane like covers 100% of the second dimension, but if you fill less than that because you have empty space in here, then it's going to fill less than that space. All right, what about number 14? So we know that the Koch curve, the one with the triangle interrupting it, had a dimension of 1.26, and the Sierpinski triangle had a dimension of 1.58. Again, I'm running 2 decimal places. I don't know why I randomly switched. I apologize. What features can you guess about a self-similar fractal that you've never seen before that also has a dimension, and this one is 1.76? We'll notice that it's getting higher and higher every single time. Let's go ahead and compare the Koch curve and the Sierpinski triangle, because those both came from page number 1. So on page number 1, we had the Koch curve down here, which had a dimension of 1.262, and then we had the Sierpinski triangle that had a dimension of 1.585. Notice that this fills less space, and now it fills more space. So I would expect something that has a higher dimension to fill even more space, and that's kind of what I'm asking you to say. It will fill even more space than the Sierpinski triangle. Or if you take the reverse of that, it will have even less empty space, right? What about number 15? How can a curve like the Hilbert curve, which is just a line, have a dimension 2? And that's the mind-boggling part of those space-filling curves. And I would say something along the lines of, it uses the power of love. No, just kidding. Of infinity to infinitely compact lines until it is a plane. If you have an infinite number of lines, even though they have zero width, 0 and infinity, they somehow merge together until you have a plane. Still kind of crazy. I don't think I have a full 5 out of 5 understanding on that one. It's just still, I'm trying to wrap my head around it. It's crazy. So what do you think fractal dimension measures? That's kind of like a really good exit ticket, right? What does a fractal dimension measure? It measures a lot of things. Like when we talked about the coastline problem, you can say it measured roughness, but here it's very specific. It measures how much a fractal fills space. If it fills space, that's a dimension of higher than 2, then it's starting to enter into the third dimension. If it's filling a space that's higher than 1 but less than 2, it's spilling more space than a line but less space than that plane. All right, time to make my own fractal. Oh, there's so many different ones that you can make. I've shown a bunch of them in class already. I've done really silly ones where you start and you just say, oh, I have a heart, and then that heart turns into 4 hearts. And they do kind of all have to touch, and you can say, oh, and then it keeps going on and on and on. I'm going to do a few just so you can choose and pick your own. Well, you can say that one's going to be log, okay, well now there's 4 hearts instead of 1, and each of those hearts is 1/2 the size. It's 1/2 in that dimension, 1/2 in that dimension, so it's going to be log of 2. And oh, look at that, we have a space filling curve because it's a dimension of 2. If I go to infinity, I'll just completely have a plane of pure hearts. I don't know if that fits the exact definition of a fractal, but it's pretty darn close. What's something else you do? You do something that has, maybe it starts with like a T, right? I don't know. I think I'm going to run out of creativity after this one, guys. I have a cross, and then that cross is going to have, here, let me just build one shape because I'm being lazy. Then the next shape is going to be a different color. I'll say the next one has like mini crosses coming out the edges of it. And this cross has something that comes off the edge of it. You're just doing the same shape over and over in unique ways, right? That's the whole point of these self-similar fractals. And as I write, I should just mention that real life, nature, doesn't have a whole lot of self-similar fractals. Yes, they might, but it's not to be expected. It's usually a purely mathematical concept. Having all these perfectly self-similar fractals is way too mathematical and doesn't really apply to the real world. Might as well one more layer. I'm going to do like a tiny plus on each of these and say that that one also has stuff that comes, that's interesting, isn't it? Because you can't go back inside of here. So while this one had 4 pieces, 1, 2, 3, 4, I can't come back in here. I'm wondering if I've made myself too hard of a fractal. Comes out right here. I might have to make it easier for myself and cheat a little bit. We'll see how much cheating this requires. Yeah, let's go ahead and cheat. I'm just going to put one on the inside as well. Sure, why not? It's my fractal. I get to do whatever I want with it. There, ta-da! And I'm going to keep doing that over and over again. Okay, so what does that mean? Well, I had one shape that turned into 4 shapes. So I'm going to say that this is going to be log of 4 unique shapes. And then each of them has 4 more shapes, so that's why I added another 4 instead of another 3. And then how big are each of those? Well, it's definitely not half as big. I'm going to say that this cross fits perfectly in that square, and that cross fits perfectly in that square, and that cross fits perfectly in that square, and that's like 1/3 length, so it's going to be log of 3. That's just how I've defined it. You can define it however you want. And I don't know, haven't I done a log of 4 divided by log of 3 somewhere before? Log of 4 divided by log, oh yeah, it's the Cantor dust. Log of 4 divided by log of 3, so it's 1.262. Come over here, 1.262. 1.262. I approximated, so I can't say equal to. It's roughly equal to 1.262. Yeah, choose whatever fractal that you want. Calculate its own dimension. Have fun, guys. That does conclude our lesson on perfect self-similar fractals. Thanks for watching.